Can you all hear me? Hello? Can you all hear me? You can hear. Okay. Good. So now. Good. Yesterday we saw that these rooms which are the same as the Eigen Values, but now there are two Eigen Values, right? Because you have a maximally, the Karpov algebra is two-dimensional, so you have two independent generators in the Karpov algebra. So you can ask what are the Eigen Values with respect to each of them. So there will be two Eigen Values, right? So therefore you plot the Eigen Values in a two-dimensional plane. And we saw some very nice pictures, actually this regular hexagon which comes out. But the fact that
Professor,
sorry, repeat that again. Hello?
I think they cannot.
can you put the mute mic?
Near to the mic.
Mic is muted.
There is no mic here. This one here is a turn. So if I'm near here, you can hear, is it? Can you hear now? Oh, I see. It was. Okay, now do you hear?
Yes.
Okay. Yeah, so we saw these nice pictures of regular hexagon, but regular hexagon is just because we chose some convenient basis. You know, we chose the two things which we call, I think, lambda 3 and lambda 8 as a basis. It's okay. Okay. Yeah, sorry. Yeah. But now let me try to use a different basis that is convenient for some other reason. And so I will be, where's the chalk here? Yeah. So let's again do this same thing here. And so let me use some notation. So I'm now looking at the page number 51. Page number 51 of the lecture notes. Okay. So we call H1 as E11 minus E22. Remember this notation, the Eij was a matrix, was a matrix with just the ith row, and the jth column. So only this element is non-zero, and it's 1, and everything else is 0. Everything else. Huh? So in other words, I can write it in the following way, convenient way. Eij, this labels a matrix. It is not labeling the row and column. But every matrix will have a label which will be K and L. So K labels the row and L labels the column. Then what we are saying that since everything else is 0, only that is not 0. This is the same as delta Ik and delta J. Right? So it says that only when K is equal to I and L equal to J, only then it is not 0 and it's equal to 1. Otherwise, it's all 0. So this is a shorthand notation for this. Instead of writing this matrix all the time, this tells you. So this we used already yesterday. And we saw the commutation relations between the Eij and I prime, J prime, and so on and so forth. So we can conveniently use this notation to write down all the Karpov generators as well as the eigenvectors. We can do that. So the H1 was E11 minus E22. This was already what we were using. So it's 1 minus 1, 0, 0, 0, 0. But instead of using lambda 8, we'll use H2, which is E22 minus E33. Okay. So this will be, so this is like sigma 3 in this 2 by 2 block. This is sigma 3. And here we just choose just E22. So here it's 1, minus 1, 0, 0, 0, 0. So in this block now, in this 2 by 2 block it is sigma 3. Okay. Of course, you could have obtained lambda 8 by choosing some combinations of them. Okay. Yeah. Okay, some particular combination you can choose to get lambda 8. Lambda 8 is just a, so this spans, these two generators spans the Cartan subalgebra. So this you can choose as a basis for Cartan subalgebra. Then the remaining guys I will write. So the remaining ones were the remaining 6 of them. We could find combinations which were eigenvectors of this, right? Eigenvectors of the adjoint representations of these two generators. Actually, we were using lambda 8, but since lambda 8 is a combination of these two, you can equally well talk about the eigenvectors with respect to these two, right? So the eigenvectors were, I mean, E12, E13, E23. These were what we called the positive roots. This was just a convention. I mean, we just chose a convention to call this as positive roots, positive root vectors. There is a terminology which I should just mention. The roots are the eigenvalues. And these are the eigenstates. Those eigenstates are called root vectors. Okay? This is just a terminology. It can be a bit confusing because root itself is living in a 2 dimension. Remember, I mean, there were two eigenvalues. So we were drawing roots in a 2-dimensional. So that also looks like a vector. No, it is a vector, but it's a vector in a different sense. It's a vector in 2 dimensions. Okay, this is a root vector. These vectors are living in the 8-dimensional space of the SU2 Lie algebra. Right? So it's just a terminology. So please don't get confused. When I say root vector, I really mean this. And then we had the transposes of these things, 2-1, E31, and E32. E32. These were again, we were negative root vectors. I mean, these are root vectors. The roots, these roots, okay, so what are the roots? Let's write down. In fact, okay, so E12, so we will give another notation here. I'll call it X alpha 1. Okay. Alpha will be the roots. So alpha will label the eigenvalues. Alpha will label the eigenvalues. So this will label the eigenvalues, the roots. Roots meaning the eigenvalues. So that is the eigenvalues. Values, because there are two independent eigenvalues. Okay. So this X alpha 1 is the same as E12. X alpha 2 will be E23. And X alpha 3 will be E13. Okay. And then these will be the corresponding negative ones. I will denote them as X minus alpha 1, which is E21, X minus alpha 2, which is E32, and X minus alpha 3, which is E31. Okay. So now we can find exactly what are these alphas. So what we want to ask is, if I look at the commutator of any H, so let's see, the symbol is H. So H is an, so I should write that. So I will call, let's see if there is any notation for the Cartan subalgebra. Yeah, I will again call, so the Lie algebra itself, SU2, SU3 Lie algebra itself, I will denote it by G, curly G. Capital G is a group. Capital G is a group, this script G or whatever. Yeah? This G I will denote for the Lie algebra. And the Cartan subalgebra I will denote it as, I will denote by, let's see, curly H. I don't know, curly H. Okay. So this is 8-dimensional for SU3, and that is 2-dimensional. Cartan subalgebra. And for this script H, I have chosen these two bases, H1 and H2. So H1 is this, H2 is this is H1 and H2. Okay. So an arbitrary element, this means an arbitrary element let's say H belonging to script H, curly H, whatever, can always be expressed as a linear combination of these two, right? Because this is the basis. So let's call it, so H will be, for some numbers, let me use again the same notation. Yeah, let's call it A and B. A H1 plus B H2, where A and B are some numbers. So any Cartan subalgebra element I can express as a linear combination of the two. That's right. So what we now want to find out is the eigenvalues, the roots basically, right? So in other words, we are looking at H commuted with, say, X alpha 1. Let's look at that. Let's look at this commutation relation. So whatever it will appear, if this is an eigenvector, it's going to be again X alpha 1, and then some number. That number will be the eigenvalue, right? So that number, I will write it in this way. So alpha of H. Because that number that you will get will depend on which H you chose, right? For example, if I had chosen simply H equal to H1, it will be some number. If I had chosen H2, it will be another number, okay? And in general, I mean, so, yeah. So this is the thing. So we want to find out what is this alpha H.
If H is arbitrary, right?
If H is?
Arbitrary, so we are estimating that combination both, right?
Yeah, so it will be this number will depend on A and B, right? Because if I had just chosen H1 commuted with that will be some number times X alpha 1. So if similarly H2 will be some number, right? Now if I take this one, it will be A times the first number plus B times second number, right? Now there's an exercise here, exercise 8.4. It's very simple. I mean, you just have to just work out that using the commutation relations for the EIJs, you can work out, and that's exercise 8.4, which says that alpha 1. So this is alpha 1, right? This number 1, this 1, 2, 3 just labels, there are different roots, no? So this just labels the different roots. So this is for alpha 1, and similarly for alpha 2 and alpha 3, etc. No? H X alpha 2 is the alpha 2 H X alpha 2, and similarly for alpha 3. So this will be so this has the information about the eigenvalues, this quantity. So the alpha 1, so the thing to prove in exercise 8.4 is that AH1 plus BH2 is 2A minus B. Alpha 2 of AH1 plus BH2 is minus A plus 2B. And finally, alpha 3 of AH1 plus BH2 is A plus B. So this is just a simple matter. I will just do one of them and then you do the remaining ones. Just one to see that, I mean, how it works. Although you already know it. So let's just look at alpha 1. So I want to look at X alpha 1, E alpha 1 was, X alpha 1 was E12. So we want to look at the commutation relation of this with the say, let's take H1 first, or AH1 plus BH2. What is AH1 plus BH2? So there's A here, minus B here, right? So you multiply by A, and then multiply by B and add that up. Okay. So you get here A, and then here you get B minus A and minus B. So B minus A and minus B, and everything else 0. Okay. So I have to take the commutator. So if I multiply, if I have two terms, this times that minus that times this, right, commutator. So if, let's look at this way. So I'm going to get first, so this way, I mean the first term, this times that will be, okay, this will be 0, that is A, 0, and here you get 0, B minus A, this everything is 0 here, right? Because the second guy is absent. And the last one is also 0, so that's that. That is when you multiply this way. Now I want to multiply this times that, right? So order has to be changed. This comes here. Huh? So that means I have to take the row here and multiply to the columns here, right? So when I multiply, so there's a minus sign because commutator means there's a minus sign. If you multiply here, this gives you 0, but
0 P minus A and the rest is 0.
Sorry, repeat that again.
0 and then P minus A and then the rest is 0.
Ah, so yeah, repeat again. So 0,
0 P minus A.
B minus A, and
0. Oh, the rest is 0.
That is strange. Yeah, okay, B minus A, fine. No, there's something's wrong here. Yeah, okay, that's okay, yeah. And 0, 0, 0, everything else is 0. Okay, so what do we get here? So this whole thing I can add that up. So minus plus A, so 2A minus B. So this is the same, so this result is the same as 2A minus B times x alpha 1. Right, because this is 1. I mean, you take out A and B minus A, the same as 1. Right? So therefore, this quantity is, yeah, that is that statement. Okay. Similarly, you prove the others also. Okay. So this is now there is a reason for this notation. It really should be thought of in a more abstract way. What it means. Can you place this part? What you should think of is the following. So this quantity, when we write something like this, so this is a vector space. Okay? And what is alpha? I mean, this is a number. This is a number. This whole quantity is a number, right? Like here. This is a number. Okay. So given a vector H, which means I have specified A and B, no? Given an element of this Cartan subalgebra, which means I have specified A and B, alpha 1 acting on that just gives you this number. The number, right? So alpha should be thought of as a map from H is a Cartan subalgebra, of which this is an arbitrary element, to numbers.
So it's like a tensor component?
Basically it's a function. It's a function on the, a function is what? Function, when you say a function on some space, right? Say f of xy. F of xy is a number. Right? So f is a map from, in this example, xy is two-dimensional space. Every point of the two-dimensional space, this f is associating a number to it. And the number is f of xy. Right? So it's really a map of, so this alpha is a map from the Cartan subalgebra to numbers. Okay. On the other hand, I mean, but this is not an arbitrary map. It's a linear map. This map is not an arbitrary map. It's not. It's a very. I mean, not an arbitrary map. Okay, it's a linear map. It's a linear map in the sense that if I take some element H and H prime, say two elements of the Lie algebra, of the Cartan subalgebra, then alpha of H plus H prime, okay, because this is Cartan subalgebra is a vector space, so of course you know what it means to add in the vector space, right? You can, it's defined. is an element of. This is the same as alpha of H plus alpha of H prime. That's what means a linear action. Now, you see, just to contrast that, this is a very strong condition. Because you see, when I said, like I gave an example, function of variables x and y, let's say. So I have a plane and I'm writing down a function. Now, if I had chosen the function of f of xy, x comma y, to be equal to say x squared plus y squared, this is not linear, right? Because if I choose another, so xy was a point on in the two dimension. This was xy. Right? Now I can choose some x prime, y prime, another point. So then, if I add these two up, then the new x coordinate will be x plus x prime and y plus y prime, right? So if you look at now f of x prime, x plus x prime, comma y plus y prime, this is not the same. This is not the same as f of xy plus f of x prime y prime for this function, this quadratic function. This quadratic you can easily see. So, linear means, linear function means that only thing that is allowed is something which is linear in x and y, right? So the most general linear function, f of xy, which is linear, is something of the form, let's say, ax plus by, plus possibly a c, a constant. But that constant is not allowed because we know this roots are satisfying the condition that alpha of 0 is 0. Right? Because if this matrix we have chosen to be zero matrix, that is the zero element of the Cartan subalgebra. So just take A and B to be 0. And of course, everything is 0. 0 matrix times, that's 0, right? So in this case, it's linear. And of course, there is no such constant term floating around. So in other words, also we have the condition, that alpha of 0 element is equal to 0. So the linear. So such space, so these are called, I mean, when you have a linear map from a vector space to numbers, then these linear maps itself forms a vector space. Okay. This itself forms a vector space because if I take two linear functions, just to think again about that, if I take one linear function f1 of xy and f2 of xy, then if I can talk about an f1 plus f2 xy, or any number, let's say c and d, any number times f1 plus any number times f2 xy of xy, which is simply defined as c times f1 xy plus d times f2 of xy. So since this is linear, that's linear, the combination is also linear. So the set of all, if I just look at the set of all possible linear functions, no? Linear functions, then that itself forms a vector space.
So we can do it vice versa? We can map from H to R, right?
Yeah.
We can think of it as a dual vector space?
Yeah, exactly. So therefore, according to this, then what we are saying, since alpha itself is also a vector space, alpha belongs to a vector space again. So alpha belongs to the dual vector space, and dual vector space denoted here by H star, right? Yeah, H star. H star is a dual vector space. Is the dual vector space to H. So it's a dual vector space. One important point is that dual vector space has the same dimension as original vector space. And that's easy to see because, I mean, I have this vector space structure there, right? So again, I can choose a basis for this vector space, right? So if I, okay, so to give the example here, I mean, again, going back here, I mean, if I give you so let's suppose I've chosen some basis, H1 and H2. Or in general, I mean, say in any dimension, n-dimensional space. I mean, here we are talking about two-dimensional because Cartan subalgebra is two-dimensional. But this statement is completely general. And I'm trying to prove it in generality because when we discuss generally algebras, it will be any dimension. No, this will be any dimension. Cartan subalgebra could be any dimension. No? So that's why I just wanted to show you this. So let's suppose I have n-dimensional space, original space here H is n-dimensional. Then I can choose a basis H1, H2 up to Hn, right? In this basis. Now I want to write down the most general functions on this. So it is sufficient for me to, so let me define the functions, some specific functions. I don't want to use this alpha, let's call it beta. I don't want to confuse with that symbol. So let's say beta is a function. I will denote beta I, I will call beta I, this is a definition, I'm defining a function, beta I. So it's clear that if I can define how any function acts on H1, H2 up to Hn, then I know how it acts on everything because it's linear, right? So if I know what is the say beta of H1, what is beta of H2, what is beta of Hn, then since any vector can be expressed as a linear combination of them, right? I mean, let me just say. So let's say beta, I know what is beta of H1, beta of all the Hi, I going from 1 to n. Say this I'm given. Somebody has given me, okay, beta acting on this guy is something. Okay? Is let's say, I don't know, Xi. Okay. Then this defines uniquely an arbitrary element. Arbitrary element is simply A, I, Hi, right? Because this is the basis. So any other element can be expressed as a linear combination. So this I. So this is an arbitrary element. Well, this is going to be by linearity, by the linearity condition, it's the same as sum of I, Ai, beta of Hi. Right? And since this I know already, somebody has given me these numbers, no? So then I know how it acts unambiguously on any element or a vector space. Okay? So that's the one thing. Second thing, so notice is that, so now I want to write down a basis for all possible linear functions. And so if I can show that the basis, again, basis of all the linear functions is again n-dimensional, then that shows that the dual space is again n-dimensional. Right? That is the idea. So how do you do that? So let me define some specific functions. Beta I, I will denote by beta I. It has a property, so this is a definition. I'm just defining these functions. Beta I on Hj equal to delta Ij. So I just define these functions. And then extend it to all the arbitrary elements by using linearity. Because once I have defined this, then from this argument, we can extend it to all the vector space. Right? Now this is enough. Because now you see this beta, I can write beta is simply xi beta I, sum over I. This arbitrary beta, this beta which I have defined, this is arbitrary numbers, xi. Okay? This beta is nothing else but linear combination of these beta i's. Because we can just check if beta acts on Hj, okay, then it's the same as summed over I, xi, beta I acting on Hj. But beta I acting on Hj, we have defined it as delta Ij. Okay? So xi delta Ij summed over I, that's the same as xj. Right? So you see, I could reproduce these functions, beta, this function beta, as a linear combination of these beta i's. And this was completely arbitrary function, linear function. No? So any arbitrary linear function can be expressed as a linear combination of these special functions that I have defined. But how many of them are there? There are precisely n of them. Right? So that means the dimension of the dual space is also n. Is n-dimensional dual space.
Isn't this trivial?
It's trivial. Yeah, it's trivial. Yeah.
Right?
Yeah, it's trivial. Yeah. But I mean, many times we don't think in terms of this, in this language. No? But this is a general. But sorry, I interrupted you. What were you saying? Because?
No, I was just wondering, is it possible to have a mapping between a dual space and a vector space, and the dimensions are not equal?
No, it's not. I mean, yeah, this is a proof, in fact, yeah. But I mean, this is usually taught in the linear algebra course. I mean, but I'm just trying to repeat it just in case, because maybe this was taught in the first year of undergraduate, so probably some people may have forgotten about it. Okay, so this is, so one should really distinguish it. So alpha is in the dual vector space. That is the way to think about it. I mean, yesterday we were not thinking like this. We were just explicitly computing the, right? But really one should think of that. Alpha is in the dual vector space. And that is why alpha is two-dimensional, because in SU3, the H was two-dimensional. I mean, the H, Cartan subalgebra was two-dimensional. Alpha lives in a dual space. The roots were living in dual space. That's why we were able to draw the roots in a two-dimensional space. No? Well, it is trivial because, of course, there are two eigenvalues. Okay, so now, so given this, so assuming that you have proven this, there are some nice features here. So, can I erase this part now? Okay, erase. There are, first you can see that there are subalgebras. For example, SU2 subalgebras, which we have again seen last time. So there are SU2 subalgebras for every non-zero roots. By the way, so if for alpha 1, alpha 2, and alpha 3 were that, I mean, this we obtained by looking at this. I mean, you can also show that, so I mean, yeah, this was what we saw, of course. But okay, I'll come back to that. So SU2 subalgebra, how many SU2 subalgebras are there? There is one which is H1, X alpha 1, and X minus alpha 1. Yeah, I mean, I remember, yesterday we saw that, right? I mean, you have this E21, E31, E32. This we called, these were negative roots. The positive roots were E12, E13, and E23, right? And we saw that eigenvalue of this and eigenvalue of this were opposite signs, right? So that is why for every root alpha 1, there is alpha 1, alpha 2, alpha 3, there will be also the negative roots. Minus alpha 1, minus alpha 2, minus alpha 3. Okay. That's the structure. So this forms an SU2 subalgebra. So this X minus alpha, negative root, negative of the alpha 1. So this is one SU2 subalgebra. We saw that yesterday. Subalgebra. And another one you could write it as H2, X alpha 2, X minus alpha 2. This is again another SU2 subalgebra. And you can also write down, for example, H1, you could write down, if I take H1 plus H2. H1 plus H2 was simply 1, 0, minus 1. Right? H1 was 1 minus 1, H2 was 1 minus 1. So when you add that up, this becomes 0, and you just get 1 minus 1. And so H1 plus H2, together with X alpha 3 and X minus alpha 3. This also is another SU2 subalgebra. So just to relate it to the yesterday's picture, which was drawn, which was like a hexagon. Yesterday's picture, we are talking about, this is X alpha 1, This is x alpha 2, and here is x alpha 3. And the negative ones are x minus alpha 1, x minus alpha 2, and x minus alpha 2, minus alpha 3. Okay. So what this is saying is that if I draw these lines here, so which is passing from the origin, okay. So this x alpha 1, x minus alpha 1, and h1, here you should think of this as like the Cartan subalgebra is sitting here, right? Because Cartan subalgebra, of course, commutes with itself. So those are like the zero eigenvectors. So x alpha 1, x minus alpha 1, and h1. This forms one SU2 subalgebra. Similarly, x alpha 2, x minus alpha 2 this is another subalgebra, and this is another SU2 subalgebra.
Each of them is three-dimensional?
Sorry, repeat that again?
Each of them is three-dimensional?
Each SU2 subalgebra is going to be three-dimensional, yeah. I mean, that's SU2 subalgebra, yeah. But again, as pointed out yesterday, these are not, I mean, they don't commute with each other, you know. So it's not some direct sum of SU2s, no. So this is very complicated, I mean, there is intertwining. These different SU2s are intertwined with each other. So for example, we saw the commutator of x alpha 1 with x alpha 2 gives you x alpha 3. Okay. And so on. The other thing we yesterday noticed, I'm just summarizing again, is that if I take a commutator of the two eigenvectors, any of these eigenvectors, any two of them, then the result is going to be another eigenvector whose root will be the sum of the two roots. Right? It's additive. We saw that yesterday. Because this is a very important property. So if you have any question, any of you have any question on that, I should go through it again. Because this is really the most crucial, one of the most crucial things. That, and let me just write it down so to remind you. So if I have two roots, if I have two root vectors, say x alpha and x beta, let's say, two root vectors, then the commutator of x alpha, x beta is going to be something. So let's see. The first question was whether this is a root or not. So remember, what was the meaning of that? This meant that, so when you say this, what does it mean? This means x alpha is alpha h, x alpha, and x beta is alpha h, beta h, x beta. So now let's take the computation. So to ask whether this is an eigenvector, so question is it an eigenvector? Or is it a root vector, let's say? So to do that, I have to just do this, right? Just look at the commutation relation of this object with x a with h. Then use the Jacobi identity, and that's the same as h x alpha, comma x beta, plus x alpha, h x beta. Okay. This is due to the Jacobi identity. What is this? This is due to Jacobi identity. But this I know, this is alpha h times x alpha, that is beta h times x beta. These are numbers, I can take them out. So that's the same as alpha h plus beta h times x alpha x beta. Okay. So that means this is a root vector, and the corresponding root is simply alpha plus beta. Because we saw that this alpha and beta live in the dual vector space, right? So it's also the addition, alpha plus beta makes sense. So that means the corresponding root is actually alpha plus beta, the root of that. So in other words, this should be, according to our notation, because this is what is labeling the root, so this is nothing else but x alpha plus beta. Okay, some number times x alpha plus beta. Proportional to this, proportional. But then, I mean, so of course, I mean, it could be that alpha plus beta is simply not a root, like in this picture here, right? If I take and say alpha equal to alpha 1 and beta equal to alpha 3, then if I add these two, I should get some point here. These two, alpha 1 and alpha 3, if I add, I should get a point here. But that point simply doesn't exist. Okay? So that means it should be 0. I mean, this would be 0, the commutator would be 0. Okay? On the other hand, if I take alpha equal to alpha 1 and beta equal to alpha 2, the sum of these two vectors is that. So x alpha 1 with x alpha 2 commutator is going to be some number times x alpha 3. Okay? That number could be 0, of course. But I mean, this argument says that this is proportional to that. No? But that proportionality constant could be 0. So that you have to check explicitly. Explicitly check, knowing what is x alpha 1 and x alpha 2. You know, those are just I erase that E12 and I think E23. Just take the commutator and you'll see that you will get the E13 with a non-zero number, non-zero coefficient. In fact, we will prove in the next next 2 weeks that this is the general statement, that if the root exists, then the proportionality constant is not 0. Okay? That will be a general statement. We will prove that. But here we can check explicitly. No? For SU3. That is not 0. So therefore it is intertwined, you see. There's one SU2 here, there's another SU2 here. But when I take the commutator of these two, I get that, you see. So it's not, they're kind of very tied up in a very complicated way, these two, the three SU2s. Okay. So this fact is pretty important. So, I mean, from there we can directly, I mean, from this, looking at this diagram, we can immediately start adding and see what is definitely 0 and what is not 0, and what commutators are 0, what commutators are not 0. Okay. Now, what is the use of this? I mean, the fact that there are all these SU2s is the usefulness is there because we know completely everything about SU2. Right? I mean, that was the first part that we studied. We know everything about SU2. We know all the irreducible representations of SU2. So, therefore, using this knowledge, we should be also able to compute all the irreducible representations of SU3. Okay? So, let me just state that little. So, what does it mean here? So, in SU2, remember, we had for SU2, we had, I think, I don't know what we were calling. Well, let's just say, okay. So, we had, I don't remember what was the notation. But anyway, we were calling what? Maybe we were calling x plus minus. X. So we had this h, x plus was some number times x plus. Okay, that number depended on the normalizations of this h and x. H, it was dependent on normalization of h. I think we were using sigma 3 by 2, right? We were calling sigma 3 by 2. In that case, this number was just 1, right? If I didn't have if I had just sigma 3, which is the case we have defined h1 and h2 as just sigma 3, without this half. No? Sigma 3 in that 2 by 2 block. H1 was 1 minus 1, 0, 0, 0, 0. So this is h1. Right? So if you think of this 2 by 2 block, it's a sigma 3 then.
Yes, actually, I was going to ask you about this purpose. Why do you think is this shape exactly? I know it has to be diagonal. Why it is not, let's say, 1, negative 1, 1, negative 1, 1, 1. Why one of the improvements had to be 0?
Because trace had to be 0, no? Trace is 0. These are, yeah, this trace is 0. The SU3 is a trace. If you didn't have trace condition, then of course, to this H1 and H2 that we defined, I could also add another H3 which is simply the identity, right? Just the identity matrix, everything else 0. But this H3 is trivial because it's going to commute with everything, no? So that is why U3, this would be U3. If you don't have tracelessness condition, that means at the level of group, you're not imposing determinant equal to 1 condition, right? So this would be the U3, and in U3, basically it splits into U1 plus SU2, where this is a direct sum, meaning this commutes with all of it. It's a direct sum. Direct sum is the analog of the, I remember I defined to you direct product of the groups, 2 groups, no? Direct product of the groups. But then when you look at the infinitesimal version of it, that translates itself into direct sums of the Lie algebra. So if I have a group G1 and a G2, and I take the product of the 2, direct product of the 2, and then you look at the infinitesimal version of it, that would give you a Lie algebra, which is the Lie algebra of G1, direct sum Lie algebra of G2. So this becomes, So this, I mean, even if you add it, it's of no, I mean, it completely commutes with everything else. So, okay, so, yeah, what was I saying? Yeah, so, I mean, so remember in this SU2 case, what we did, incidentally, remember that here, let's look at this one here. If I take the commutator, remember that these two are forming an SU2 subalgebra. We said, this is something you should check it. I mean, yesterday we did it, but just check it yourself. But what we found was that in this case, x alpha 1, x minus alpha 1 commutator. First of all, we found h x alpha 1 was x. So what does it mean? So that is the same as alpha h1. Sorry, h1 alpha h1 alpha 1 h1 times x alpha 1, which according to that you just put b equal to 0 and a equal to 1. That is 2. So this is 2x alpha 1. But that 2 is precisely coming from this fact that you see this is really sigma 3. In that 2 by 2 block it was a sigma 3, not sigma 3 by 2. Right? In SU2 also, if you had taken just sigma 3, you would get a 2 there. No? So the fact that we were getting 2, and that is why this axis we had put here 2, 0 was a thing. But that was because we chose it to be sigma 3. Okay? Because of that, if you now look at it, all the representations of this SU2, we know all the representations of this SU2, we have studied that. No? We know that if I had chosen sigma 3 by 2 as my H, then all the representations are labeled by, all the irreducible reps are labeled by J, by the spin J, right? Where J can be integer or half integer, right? But now we are not using sigma 3, we are using not sigma 3 by 2, we are using sigma 3. Okay? So that means it will be twice this eigenvalue now, right? Because now we are choosing this H1 to be analog of sigma 3. Analog of sigma 3. Or a 2 by 2 block inside the 3 by 3. Right? Sigma 3. So therefore, eigenvalues here would be 2 times the eigenvalues that you would expect here. Right? So that is why this factor of 2 is there, right? Because you know the adjoint representation of SU2 is spin 1 representation. J equal to 1, not 2. Right? But this is exactly J equal to 1. If you are divided by 2, then it would be 2. Right? It will be just that. So this will be H1 by 2 will be that. So this is exactly the commutation relation which you had for that. So this was the raising operator of SU2 and the lowering operator was X minus. Okay. So the upshot is that in this normalization that we are using, the spins, these quantum numbers are always going to be integers. Okay? Even for spin half representations, this will be 2 times half, so integer. No? Okay. So in this convention that we are using, any irreducible representation of this particular SU2 subalgebra will be labeled by integer eigenvalues. No? And in particular, the highest weight will be some non-negative integer. Will be labeled by a non-negative integer. As opposed to the SU2 when we studied, it was labeled by a non-negative half integer. I mean integer or half integer. No? But now since I am multiplying by 2, this will be all integers. And the same thing with the H2. H2 also, everything was sigma 3. So all this, so what we are saying is that, suppose now I want to construct some representation of SU3. Okay. But I mean, so I can ask the question, some other representation, not adjoint, some, let's say, fundamental representation, or even any representation. Since it is finite dimensional, this is a point I should mention more carefully. Yesterday again I mentioned this. So let me just repeat that again. We saw one nice property here is that when I took the commutator of any of these 2 guys, then the roots added up. If I look at the commutator of x alpha 1 and x alpha 2, the result will be again a root vector, but with the root being alpha 1 plus alpha 2. It was additive. We saw that just now. We saw that, right? The same extends also to any representation. So suppose I have some representation, okay, and I look at H1, RH, and suppose I diagonalize this Cartan subalgebra. So I can again in any representation I can diagonalize this. No, so if I call this some state psi inside this representation, okay, this notation I hope is not confusing. No, this is just if this representation has some m dimension, then there will be m such vectors, m such linear independent states. So this will be some number which again will depend on h, which will be again in the dual h star space, h star space. But it will not be those alphas. Okay? It will be some w. Let's call it w. W active on h times psi. Right? I mean, this simply means that if I take, so this will be like W1 H1 plus W2 H2. If I write H equal to AH1 plus BH2, then since it's again linear, this linear function, so this is going to be ARH1 plus BRH2 acting on psi. But that's going to be, say, some A times W1 plus B times W2. So W will have again 2 components, W1, right? So this acting on psi. So these are called weight vectors. Okay? Those were called root vectors. So these alphas were called root vectors. Alphas were called root vectors. Roots. This is not root vectors, roots. W's are called weights. Just to distinguish. I mean, after all, adjoint representation is also one of the representations. So root is also a weight, but of the adjoint representation. So because adjoint representation is something very special, we just gave it a different name, root. So, but this is a weight. It's a weight, okay? And so you can do that. You can diagonalize all the m-dimensional space in terms of the eigenvalues with respect to h. But the question that we are asking is that, okay, now I have done that. So let's say I take this one of this psi and apply r of, say, x alpha 1, for example, on this state. Okay? In fact, let me just label this by w. That will be better. So this psi is, I just label it by w being the eigen, by the weight, being the weight. It's better too. That convention is better. Okay. So I want to ask the question, what happens to this? What is this thing? Is it an eigenvector again of RH? And if so, what is the eigenvalue? So this is the first question. And so let's apply RH on this to see whether it's an eigenvector. And then again, the standard trick we use. This is a trick which we all continuously use. Write this as a commutator, and then the extra piece. So the commutator psi plus Rx alpha 1 RH psi W. I'm calling this W now. Now this term is simply alpha 1 of H, right? This is alpha 1 of H times Rx alpha acting on W. Can you see it from it's not obstructing you, right?
Yes.
It's obstructing, so maybe I should write on the top again. Maybe I use this part. So we wrote it as a commutator, RH, Rx alpha acting on W, plus the extra term, which is Rx alpha, RH acting on W. Now this term, we know that this is this just gives you the root, alpha H, Rx alpha, W. And this one, RH acting on W, we said is WH times W, right? So that, and WH is a number, so I can take it out. So it's WH, Rx alpha, W. So therefore we see that it's alpha plus W, H, and acting on Rx. So you see that when I applied Rx alpha, the weight changed, weight increased by alpha. W increased by alpha, right? W went to W plus alpha. So this is how the raising and lowering operators are working. Just like what happened in the SU2 case, right? You started with some weight, let's say in the spin J representation, if I look at mth state, then if I apply J plus or J minus, I'm shifted by M plus by 1 or sub minus 1. No? And that's what is happening. Okay. So now I can specify. So how did we then proceed with in the SU2 case? We said, okay, since we are talking about finite dimensional representations, there must be a highest weight state, right? Otherwise, you keep applying J plus on and on and on, it will keep going, right? So there must be a highest weight state. For any finite dimensional representation, there must be a highest weight state. And of course, there must be also lowest weight state. But what is the analog here? In the SU3 case, how can we say, I mean, what is the highest weight state, right? Now, what was special about J plus? J plus was we said it's a positive root. Okay? There was a positive root and J minus was a negative root. And every time J plus was applied, the eigenvalue kept increasing in the positive direction, right? Whereas when you apply J minus, eigenvalues start decreasing in units of minus 1. No? So here also it will do, I mean, at some point, I mean, so let's say if I started with some weight here in this picture. Yeah? So this is the dual H star. Right? This is the dual space. This is the dual space here. H star is two-dimensional, and I'm drawing all these vectors there. Alpha 1, alpha 2, etc. I'm drawing there. So if I apply, suppose I started with a weight W, some weight, then if I apply X alpha 1 on that state, its weight will become, you just add to this, whatever, this will be W plus alpha 1. No? Now if you apply once more X alpha 1, it will go further, and so on. So at some point it should stop, otherwise you get an infinite dimensional state. So there must be highest weight state, which is annihilated by R, in that representation. R is that representation of alpha 1. Right? And the same thing should happen also for, so idea here is that suppose I have chosen my positive, let me choose the positive roots to be this. So I draw a line like this here, and I say everything on this side is I call positive roots, and everything on this side I call negative roots. Okay? Notice that in this way of dividing, from each of these 3 SU2 subalgebras, so there was one SU2 subalgebra, another SU2 subalgebra, another SU2 subalgebra, we are picking up only one of them, you see, from each SU2 subalgebra. I call this as a positive root in this SU2 subalgebra. I call this one as a positive root of this subalgebra. So this will be like J plus, this will be like J plus for this SU2, and this, for this SU2, this will be like J plus. Okay. We will see again that these are all completely general statements, that we'll see that this is true in all the algebras that we'll be studying. That's why I'm trying to phrase it in this language, because you will identify it immediately when we discuss the more general case. The one thing that you immediately see here, that alpha 1 plus alpha 2 is alpha 3. Right? I mean, if you take this vector and that vector, you get that. Which is another way to say that when you take the commutator of x alpha 1, x alpha 3, alpha 2, you get x alpha 3 up to some number. Okay. So alpha 1 plus alpha 2 is alpha 3. So, I mean, if I have imposed already the condition that this state, there is some highest weight state, which is the highest weight with respect to this SU2 and also with this SU2, okay, that means Rx alpha 1 acting on this is 0, as well as Rx alpha 2 acting on this highest weight state HWS, highest weight state, equal to 0. Then I don't need to impose further an extra condition, x alpha 3 acting on HWS equal to 0. Why? Because x alpha 3 is the commutator of these two. Right? So if each of them have annihilated the state, x alpha 2, sorry. If each of them have annihilated the highest weight state, then this is automatically going to annihilate the highest weight state. Right? Because I also told you this coefficient is not 0. Okay? So therefore it is sufficient to take, I mean here, there's a terminology for that. So this is the positive root. The positive roots are all of them, negative roots are all of them. In this positive root, I can choose a basis. So here the basis is x alpha 1 and x alpha 2. Because x alpha 3, I can just write it as x alpha 1 plus x alpha 2. Okay? So these roots, such roots, this x alpha 1 and x alpha 2, are called simple roots. Again, we will see the precise definition later. Simple roots. So simple root from this you see is that any positive root which can be expressed as sums of other positive roots is not a simple root. Okay? So because x alpha 3 could be written as x alpha 1 plus x alpha 2. No? So this is not a simple root, but this is simple. These two are simple roots. Okay? So highest weight state is defined by just this equation. You take all the simple roots in this particular choice. For this particular choice, I chose this x alpha 1 and x alpha 2 are the simple roots. Okay? If I had chosen a different, if I chose a different positive root, suppose I had chosen this as a positive, everything this side is positive, that is negative, then the simple roots would be these two. You see? Okay? If I had defined this as a positive, that means in this SU2, this is the J plus. In this SU2, that is J plus. And this SU2, this is J plus. In that case, the simple roots will be these two. And then you would say this weight is defined by, the highest weight will be annihilated by this and that. But that will automatically ensure this, because the commutator of these two is that. So this is the way it works out. But So this is the condition, and then, so what else is required to specify the representation? The irreducible representation. So the things that are needed. So for the irreducible representation, of SU3. What we need to do is, so conditions are x of all the, x of all the, let me just say, simple, x of simple roots, acting on R of x of simple roots, acting on the highest weight state. This is the short form for highest weight state, is 0 for all simple roots. So you need to, because now you see they can move in two different directions. I mean, the weight can go this way or that way, no? And in each way you want to have be finite dimensional. So at some point it should annihilate, all of them should annihilate. Right? Otherwise it will keep going in. Maybe you stop, if you choose the highest weight with respect to only the first one, then maybe then it doesn't continue like that. But if there is no highest weight condition for this one, it will keep going this way. No? By repeatedly applying this operator. So you need to impose both these conditions. But once you impose these two conditions, X alpha 3 comes for free because of this commutation relation. So it is simultaneously highest weight with respect to all the positive roots. So that is one statement. But then you have to also tell me what are the eigenvalues of this HWS, this particular state. So in other words, I have to say what is R of H. H is in the Cartan. So H is in the Cartan. H is in Cartan subalgebra. How it acts on this highest weight state. And that will be some weight, WH. W of HWS. And maybe I can write this WH to indicate that this is the weight for the highest weight of H. There are too many H's. It's okay. No, I don't know. I'll just write WH. Okay. So this will be some weight. So this is the analog of J in the SU2. Or because we have normalized, we are using sigma 3 rather than sigma 3 by 2, it will be 2J to compare with the previous SU2 example. So this will be like 2J, but now you have several J quantum numbers. J quantum number with respect to that and with respect to that. Actually 2, because this one is automatic, because this is the commutator of these two. So you have the two SU2 subalgebras and you want to find, so both of them, H1 and H2. So it will have two components. So once you specify this, then you're done. The highest weight and this W, that uniquely defines to you one irreducible representation. Just like in SU2 case, saying that the highest weight state carries spin, the J3, I mean the H quantum number to be J, that uniquely specifies your irreducible representation. The same way here. But you need, since this is H is two-dimensional, that means I need to specify both H1 and H2. Right? Or another way to say that this H is in general, this H is in general AH1 plus BH2. So this W will be linear in A and B. So this is going to be A times, let's say, give it some name to it, plus B. Yeah, A WH1 plus B WH2. So if A equal to 1, B equal to 0, that's simply W of H1, and so on. So this information, we need to give two informations here. So we need to specify WH1 and WH2. That means in our normalization, because we are using sigma 3 by 2, sigma 3 without, not sigma 3 by 2, both of these numbers have to be non-negative integers. So the upshot is that you just give me two non-negative integers, okay? And for that, there exists an irreducible representation. For every such chart, there exists an irreducible representation of SUP. Any question on this before I start giving some examples? There are examples of irreducible representations.
Just a little clarification. For obtaining the rest of the states, we just apply the negative roots of the simple.
Yeah, exactly. Yeah, it is enough to. It's enough to just use these two, x minus alpha and x minus. Again, because this is this can be obtained by taking commutator of these two. So, yeah. So let's take, the adjoint representation itself. Let's look at the adjoint representation. What is the weight? I mean, it's just one of the representations, right? So it should also be. So first of all, which is the highest weight state? According to our this requirement. So now let's specialize to adjoint. Add x alpha 1 and add x alpha 2. Can you see, I mean, just from looking at this picture, you can see which one is the highest weight. So in the adjoint, what we are saying that adjoint of adjoint x alpha 1. Adjoint representation acts with the Lie algebra itself. So the vectors here, this ket bracket notation, that's actually the generators themselves. No? So if you take with any x, the commutator this adjoint acting on any x is the same as the commutator x alpha acting on x, right? X is arbitrary. So but now look at what are the possible x's? I mean, this is already these 6 of them and the karta, right? H1 and H2. These are the 8 generators. So if you look at that, I mean, certainly x alpha 1 and x alpha. So you want this condition for the highest weight, if this is the highest weight, and also at the same time we want also x alpha 2 acting on the same x equal to 0. If this is the highest weight. I mean, certainly this doesn't happen for the Cartan generators, right? Not with both of them. I mean, H1 is not, H1 does not, I mean, the commutation relation of H1 with this is not 0, right? And commutation relation of H2 with that is not 0. So certainly Cartan generators are not, right? And also if you look at this guy, if I apply x alpha 1, this will go here, right? That's in fact the part of the SU2 algebra. So certainly this is not. What about this? This is also not, because if I apply add x alpha 1 on that, you get that.
It must be the answer.
Must be the last one, this one, yeah. So this is it. So the highest weight here is x alpha 3. Because if you take the commutator of these two, I should get a point here, but that point doesn't exist. If I take the commutator of these two, I should get here, right? Again, that doesn't exist. So this x alpha 3 commutes with both x alpha 1 and x alpha 2. Now, what are these numbers now? This W, the corresponding weights. That was already in that exercise. You see, we said alpha 3, that exercise 8.4, I mean, these weights are nothing else but the roots, right? Because now we are talking about adjoint representation, right? Adjoint action is just the roots. So in 8.4, you saw that alpha 3, we're looking at alpha 3 of H of AH1 plus BH2 is A plus B. Okay. So if I just take alpha 3 of H acting on H1, I mean alpha 3 of H1, it is simply 1, and alpha 3 on H2 is also 1. No? Is that clear? No. I mean, what was this alpha? So we are looking at, so question now is this we are looking at this equation now. But not for any arbitrary representation, but for adjoint representation. So let's, and we have also identified the highest weight state, which is x alpha 3, right? So we just want to find the eigenvalues with respect to H1 and H2. So we want to find the adjoint action of AH1 plus BH2 acting on x alpha 3. Right? How? Add the action of AH1 plus BH2 acting on this state. So what it does. So, but that is by definition the commutator of this adjoint action is just that, right? So it is a commutator AH alpha 1 plus BH alpha 2 with x alpha 3. Okay. And this is what you are supposed to prove in exercise 8.4, that this commutator is nothing else but this is going to be, of course, alpha 3 of AH1 plus BH2 times x alpha 3. Right? This is an eigenvector, of course, and this is by definition the definition of alpha 3. Right? And alpha 3 is given in this formula. That is A plus B. So this is the same as A plus B, x alpha 3. So the eigenvalues, so now we look at these two SU2s. One SU2 was generated by x alpha 1, H1, x minus alpha 1. Other SU2 was x alpha 2, H2, x minus alpha 2. Right? So we see that if I had just taken A equal to 1 and B equal to 0, I would get 1. And if I had taken A equal to 0 and B equal to 1, again I get 1. Right? So with both SU2s, so what I was calling WH1 and WH2, in this particular case is simply 1, 1, in this adjoint case. So this representation will be labeled by 1, 1. So you can label it in this way. And you can see also, I mean, this 1 makes sense, right? You remember of this multiplication by a factor of 2, because we are using sigma 3 rather than sigma 3 by 2. So in the old SU2 language, this would be half-half. Right? But indeed, if you look at this SU2, so in the old language, in the SU2 normalization, this would be half-half. So spin half, with respect to these two SU2s. But indeed, you see that let's focus on this SU2. And okay, the eigenvalue is, we said, is plus half with respect to H1. But then when I apply x alpha 1, it annihilates it, so it's the highest weight. So I'm looking at this SU2, focusing on this SU2. And look at its action. X alpha 1 acting on that gives you 0. Again, I'm always talking about adjoint representation. So acting means a commutator. The lowering operator, x minus alpha 1 acting on that, gives you x alpha 2. Right? Because add these two roots, you get that. So you get x alpha 2. And if you further apply x minus alpha 1, it gives you 0. So this is the spin half representation with respect to this SU2. And now look at the other one, because this second, so this was with respect to the first SU2, x alpha 1, H1, which was H1 and x plus minus alpha 1. No? These are the three generators of the first SU2. The second SU2 was generated by H2 and x plus minus alpha 2. So with respect to the first SU2, we see this half means it's a doublet. No? Spin half representation is a doublet. Now looking at this second SU2, which is this one, together with H2, you see when you apply X alpha 2, it annihilates because it's the highest weight. When you apply X minus alpha 2, you get there, right? And if you further apply, it gives you 0. So this is again a doublet. This is a doublet with respect to this SU2. So indeed, it makes sense, right? I mean, so you label. So that now the thing is that compared to SU2, where you have to just label one J, one value of J. Now you need to specify two J's because you have two SU2s. So you have to specify. This is just a twice that because it's easier to write just integers, right? That's why we chose this normalization. So let's just, before I finish, I'll just take one example. So one example. I mean, the statement is just like for SU2, we said there exists a finite dimensional irreducible representation for any J non-negative, which is a half integer or half integer, right? The same statement is here. You could just specify any two numbers here, n1 and n2. These are non-negative integers. Integers because are multiplied by 2. No? And this defines to you, this information defines to you uniquely an irreducible representation. So that's what's happening with this SU3. You need two informations. And this number of information is the same as the dimension of the Cartan subspace. Two informations you need to specify the representation. Yeah. And as a result also there are two Casimirs. The Casimirs are like just, Casimirs gives you a particular number associated with a given representation, given irreducible representation. Since here in SU3, you need to specify two informations, two independent informations you need to specify to fix the representation. It is not surprising there are also two Casimirs. Right? Because if there was only one Casimir, you would say there's only one invariant of the representation. But here there are two invariants of the representation. Invariant in the sense that this labels the representation. This is not invariant in the sense that we think about, but labeling of the two information is required. No? So you need to have two Casimirs. Okay. Now let me just take the simplest example. So simplest example, okay, let's just start from, say, we take 1, 0. 1, 0. Huh? Okay. I mean, 0, 0 is trivial. 0, 0 is just a singlet. Okay. Everything spins 0, so just one state there, the 0 bit. So this is a singlet. So that is a trivial one. So the first non-trivial one will be 1, 0, or of course 0, 1. Okay. So 1, 0 means what? It means, maybe I should have drawn this picture a bit bigger. Because now this is unreadable. Let's draw this. So the picture was 60 degrees. So this was alpha 1 minus alpha 1, alpha 2 minus alpha 2. Okay. So 1. So that means H1 acting on this state. So this is the highest weight state. So this is the highest weight state. H1 acting on RH1 acting on the highest weight state is simply the highest weight state. And RH2 acting on the same state is equal to 0, because that's 0. So I'm looking at the first, this one 0. So that will be so this point, this will be actually this point here. So this is the direction for H2, right? I mean this SU2. So the fact that it is 0 means that it should be perpendicular to this line. This is because we have chosen the nice, this picture is using the condition that trace, I mean the lambda A, trace lambda A, lambda B was proportional to delta AB. But it doesn't matter. I mean, in this picture there will be exactly, so I will draw this, so 90 degrees from here. Okay. And this value is simply 1. So that means it should be exactly coming, this is 1, remember this was 1, 1. This was the highest weight was 1, 1 here, right? So this is going to be this point here. This is the half. This is the half. I mean, this was 2, 0. Okay. This was 0, 2. Where these are the eigenvalues with respect to H1 and H2. So you get this here. You start from this. Now, what happens? So certainly what I can apply here. Certainly I cannot apply this or that because that's by definition the highest weight. Right? Because this is the highest weight, it's supposed to be 0. What I can apply is x minus alpha 1. Okay. X minus alpha 1 when I apply, I'm going to come here. That is that here. Okay, this will be exactly. So this is half here. This was actually 2. So this is 1, 1, 0. So when I apply x minus alpha 1, I will go 2 units back there. So this is going to be minus 1, 0. This point. And then, now, that's it. Because you see, this 1 means what? It is a doublet with respect to the first SU2. Right? And that's a singlet with respect to the second SU2. First and second being this SU2 and that SU2. So this is a doublet with respect to the first SU2. So here you go here, but after that you cannot go because this will be the lowest weight state of the SU2. This one on the other hand, I mean if I apply x minus alpha 2, okay, that cannot be because this is the spin 0 representation of the second SU2. So that's a singlet of that. So you cannot apply x minus alpha 2 here. But now you can apply x minus alpha 2 on this state. Okay. On this state you can apply x minus alpha 2 and you get just this much, you come back here and you will come here. So this is a three-dimensional representation. After that it stops again. There's nothing. So actually, yeah, I mean, no, I should be a little careful there. This is not quite correct, because in this, you should not look at these numbers. I mean, these numbers are not the axis here. Yeah, perpendicular. Yeah, exactly. So these numbers are not. Yeah. And I'm getting a bit. I should really work with now the different diagram, not this diagram, because this was diagrammed using that, where these eigenvalues were the eigenvalue of lambda 8. This axis was lambda 8, not H2. Okay. So I should be. But at the end of the day, you will get a diagram like this. I mean, I have to make these corrections, but I will do it next time now. But at the end of the day, you get exactly these three states. And which is that representation? In fact, that representation is nothing else but what we call the fundamental representation. The defining representation. So, which was. So, in defining representation, we already know H1 R, let's say R fundamental H1 was the H1 itself, because it was a defining representation, right? So it was 1 minus 1, 0, 0. And H2, RF H2 was 0, 0, 0. This was 1, minus 1, 0, 0, 0. So now if I look at any state here, so what are the eigenvalues here? Let's see. The eigenvalues will be, what are the possible eigenvalues? I can look at 1, 0, 0, this one state. I mean, this is already diagonal, so what am I saying? H2 was this, 1 minus 1, 0. This is already diagonal, so you can read out the eigenvalues. So this will have the eigenvalue. With respect to H1, it will be 1. With respect to H2, it will be 0. Correct? Then you look at the other state. If I apply 0, 1 on the 0, 1, 0, 0, this guy will give me an eigenvalue minus 1. When I apply, this is the second, it's a second term, it will be minus 1. And this one will give you plus 1. And finally, if I apply, so these are the two eigenvalues. So 1, 0 and minus 1 plus 1. So really, this vector should be minus 1 plus 1. If you, it doesn't look here because I'm working with lambda 8. No? So you have to go back to, H2 itself was a combination of lambda 8 and lambda 3. This was lambda 3, H1 was lambda 3. And lambda 8 was some combination of H2 and H1. Right, some particular combination of H2 and H1 with some coefficients. So this picture is drawing the eigenvalues with respect to lambda 8 and lambda 3. But now what we want is eigenvalues with respect to H1 and H2. So in other words, you need to rewrite H1 equal to some number times lambda 8, H2 equal to some number times lambda 8 plus some number times H1. No? To go from this to that language. Because here I'm writing down in this notation, I'm writing the eigenvalues with respect to H1 and H2. Is that clear? So yeah. So therefore, so this is going to give you. So the second state was. Where did we say? Yeah, second state was minus 1 plus 1, and the third one is 0, 0, 0, 1. These are the three independent states. It's a three-dimensional representation, and they are all eigenstates because already in the defining representation, H1 and H2 are diagonal, so you don't need to do anything more, right? So for this one, what happens? H1 gives you 0, so this eigenvalue is 0, and H2 acting on that gives you minus 1. Okay. And in fact, you can see what is the value here. So this we said, this is the 1, 0, right? That was my starting highest weight. Now, when I reached this point, what did I do? Yeah, okay, maybe I should just work on it next time. But these are the three states. 1, 0, 0, minus 1. This point is 0, minus 1. Because you can, let's see. If I apply, we can see what states comes here. If I apply x alpha minus 1, x alpha minus 1 is this one, right? 0, 0, 0, 0, 1, 0, 0. This is x minus alpha 1. Correct? So if I apply this on that, I'm going to exactly get that state. Right? So I start from the highest weight, this is my highest weight, apply this, I get that. Huh? And so that is this state. This is that state here. So this state is 1, 0, 0. This state is 0, 1, 0. That's by applying x minus alpha 1 on that state. And finally, this state, if I apply further x minus alpha 1 on this, is going to give me 0. Okay. But I can apply the x minus alpha 2, which is 0, 0, 0, 0, 0, 0, 0, 1, 0. Right? That's x minus alpha 2. And now you see this one annihilated that. That's fine, because that we see that's why we couldn't go this way. X minus alpha 2 could not act on it, but it acts on this one, and it gives you exactly this state. Okay. So that is the state here. And that's it. After that, everything stops. Both x minus alpha 1 and x minus alpha 2 acting on this state gives you 0. So that ends it. So this is a three-dimensional representation whose weights are given here. I have to just work it out. Next time when I meet you, I will try to, this is a confusion between the lambda 8 basis and H2 basis. So I have to just go back and get this thing. Or you can try yourself during the weekend. If you look at the 0, 1 representation, this is another possibility. You can verify that has the weights which are exactly the opposite of this weight. The negative of these weights. So 0, 1 will have a weight which will start, highest weight will be here, just the mirror image of that. Okay. Here. This will be the 0, 1. And then you'll have a mirror image of this here and the mirror image of that. So this will be the representation which will be given by 0, 1. Try that during the weekend to see. And in fact, we'll also show that this guy, this representation is exactly the complex conjugate of that representation. Complex conjugate is the way we defined in SU2, right? We defined what is a complex conjugate representation. That was a general definition. So we can show that this representation, both are three-dimensional representation, okay? But this is the complex conjugate of it. Yeah. So yeah, when you work with this basis, so the point is that you need to, you see, maybe if you have another 5-10 minutes, maybe I can try to work out to see how this works out. You see, so what we said that when I apply any R x alpha on some state, then the weight of this guy will be added up, right? So W, so it will become alpha plus W. If this had a weight W, then this will go to alpha plus W. Right? So we have this already the alphas. We can see alpha 1. Again, this exercise 8.4 is crucial. So try to check that. Alpha 1. So alpha 1 of AH1 plus BH2 was 2A minus B. Okay. So which means, in this notation, where we are putting the weights of H1 and H2, weights with respect to H1 and H2, this notation, this is nothing else but 2 comma minus 1. 2, because if I put B equal to 0, so only H1, then that is 2. And if I H2, then it's minus 1. And similarly, if you look at alpha 2 of AH1 plus BH2 is minus A plus 2B. So in our notation, in this notation, we have minus 1, 2. Okay, so now what I will do is I will always use this, because this is now this eigenvalues with respect to H1 and H2. Okay. And so that notation, so I think, yeah, that is better. So let's start from there. So I start from the 1, 0, the highest weight here. Again, here the notation is again H1 eigenvalue, H2 eigenvalue. Right? That is the notation. So it's the same notation is here. Irrespective of where I am drawing it. I mean, here I am drawing it with a lambda 8 axis, but that doesn't matter. I'm just now here labeling the H1, H2 eigenvalues. So now if I look at here, and so now I apply the x minus alpha 1 on this state, and I go here. But what will be the weight of that? It will be the weight of this plus the weight of that. Right? But this is the alpha 1 has this weight, alpha 1 has that weight. So minus alpha 1 will have negative of that, right? So therefore we are saying, so this state will be 1, 0 minus 2 minus 1, which is the same as minus 1 comma 1. Okay. So that's minus 1 comma 1. And now I apply x alpha 2, x minus alpha 2. So here I'm going to get minus 1, 1 plus minus, because I am applying x minus alpha 2. Alpha 2 has that. So it's minus 1, 2, which is what? Minus 1. So this becomes 0, and that becomes minus 1. Yeah. So this is the line. This is in this language that I am labeling not H1 and lambda 8 eigenvalue, H1, H2. Then this is the correct thing. And you can see this was 1, 0. So this tells me, and this is the highest weight, right? So this tells me that with respect to this SU2, this is a doublet because this spin half, and that is singlet with respect to that SU2 because this is 0. So I will not get anything if I apply x minus alpha 2 here because this is singlet. Okay. But I will get something when I apply x minus alpha 1 because it's a doublet. The state I will get will have this quantum numbers. Okay. I cannot further go because it's a doublet. That's all. These are the two states. But now if I look at this here, that 1 says that this has a H2 quantum number 1, which means it's like in the sigma 3, I mean previous notation it will be spin half, right? Half of that will be, so it will be spin half with respect to this SU2, with the second index. This is the H2 quantum number, H2 eigenvalue. H2 eigenvalue is 1, which means it is a spin half. Right? That is why you need to apply x minus alpha 2, okay. And then you get this state here. This is again a doublet. You cannot further apply x minus alpha 2. And in fact, if you apply x alpha 3, you get there. So this is a nice picture here. Maybe I can repeat it again next time. Because probably. Yeah. Is it clearer? No, this is a. I'm saying it's just. I just use this fact that when I apply Rx alpha, the weight will add. Weight will add to that root, the corresponding root. So now I started with this eigenvalues, and this we are saying is the highest weight. So this already tells me what is allowed and what is not allowed. No? Certainly none of the positive roots can be allowed because it's by definition highest weight. Okay. So only negative roots can be allowed. I mean allowed meaning can possibly give non-zero answers. No? But which ones? Because this is spin 0 with respect to this SU2. No? So I mean any of these SU2 generators acting on that will give you 0. Right? But this is a doublet with respect to that SU2 because it's 1 here. So I can apply one lowering operator, which is x minus alpha 1. I will get this state. But that's it. I cannot go further. That's the lowest weight state with respect to this SU2. because it's a doublet. No? So it stops there. This chain stops there. There's a chain here, but it stops here. No? But now when I look at its quantum numbers, I find by just adding the weight, adding the root, this root to that weight, this root being that in this language, in the language of H1, H2 quantum numbers. Okay. This is the labeling of H1 and H2 quantum numbers. So this you add it here, you get minus 1, 1. When you add, so since I'm applying minus alpha 1, I have to subtract this minus that. Okay. So I will get here minus 1 plus 1. And then, now look at these quantum numbers here. This minus 1 just tells you, if I had normalized by sigma 3 by 2 type of normalization, this would be minus half, right? But that's okay. This was half and minus half. That's the correct spin doublet representations, right? But here I see suddenly that it has become plus half, right? Here it was 0, it has become plus half. So therefore, it cannot, there must be, I should be able to apply, so this means it's part of some non-trivial representation of this SU2 because it's carrying some non-zero quantum number. And you know that in every SU2 representation, for every positive quantum number, there should be also a negative quantum number. No? M quantum number, there's a plus, positive and negative. So there must be something with a minus 1, which is that, and that's obtained by applying the lowering operator, x minus alpha 2. And when you do that, you get 0 here. 0 for the x alpha 1. For this SU2, for H1, you get 0. So that means x alpha 1 cannot act on it. This is spin 0 representation. So this is invariant under this SU2. So it stops here. Nothing else you can do. Just 3 states.
What if you apply x minus alpha 1 again?
Where here? No, but what I'm saying is this is already just telling me this is spin 0. No? So that's, there's nothing you cannot.
It is singlet with respect to alpha 1.
Hey, sorry?
It is singlet with respect
With
to
respect to this is that SU2, the horizontal SU2.
And here, the two, one at the bottom and one on the left side, these two are shared between this SU2 in the horizontal line and the.
Repeat that again?
And these two states are shared between these two SU2 algebras.
You mean which one? This one? This point here?
This point, and yes, and the.
This is a doublet under this SU2.
Okay.
Right? This is a doublet under this SU2, and that is a doublet under this SU2. Yeah, all this is happening because these 3 SU2s which we have, they are intertwined. No? They're not acting independently. It's not a direct sum of the 3 SU2s. You can also prove this, what you're asking. So here I just looked at this number 0 and I said that this is singlet, right? But you can ask the question whether if I apply x minus alpha 1 on this, then let's see. So whether it is 0 or not. So if I look, so we are saying, so this state was already obtained by x minus alpha 1 acting on, say, let me just call it 1, 0. This state is the 1, 0 state. This state I just labeled by the H1, H2 quantum numbers. Eigen values. H1 and H2. Okay, eigen values. So then I applied x minus alpha 2, and then I applied x minus alpha 1. So now you're asking whether if I apply x minus alpha 1, do I get something? Right? That's what I. So this was my state. This state is what we call 0, 0 minus 1 state, right? That state was this, 0 minus 1. Because we reached here by first applying x minus alpha 1, then I applied x minus alpha 2. Right? So that's that state. Now your question is whether I can apply my x minus alpha 1 on 0 minus 1. Okay? I mean, the question is what happens if I apply that. So if I apply this, so then that is the same as going x minus alpha 2, x minus alpha 1, and 1, 0. Now, so the step, I mean, you should try that maybe, because now I don't have too much time. If you try to, then you try to move this across. Try to move this across, and you will see that at some point you will come to a conclusion that this has to be 0. Yeah. X minus alpha 3. Okay, we'll work out in many more examples next time. This is both of this, and several other representations. This was the simplest 1, 0. 1, 1 we already know, which was a joint representation. 1, 1. This was a 1, 1 there. Then you can ask, what about 2, 0? 2, 0. It will turn out to be a 6-dimensional representation, and so on and so forth. I mean, and then after that, so tomorrow, Monday, I will do that, and also start discussing something about the tensor products of these representations. So I'll go in much more detail, like several examples and so on, to at least illustrate the idea. What is the idea, main idea here? How you can classify in principle. It's clear that, I mean, if you start increasing these numbers, I mean, say, 5, 5 or something like that, if you try to go through this procedure, it will be very, very cumbersome, right? But the basic concept, that is the basic concept. And then, yeah, the formulas for the dimensions or representations are given in the literature. So once you specify these two numbers, there is a formula which tells you what's the dimensions. Just like for the SU2, if you specify J, it is 2J plus 1, right? Dimension is 2J plus 1, which is, if I call 2J as n, because I'm calling, this is 2J. So if you have n, then it's n plus 1 for SU2. There is a similar formula for SU3. Here you have two integers, two non-negative integers, and there is a formula for that. I don't remember the formula, but I think if I call these two numbers n1 and n2, non-negative integers, I think, I'm not sure, don't have, this formula is not given here, n2 plus 1, and probably n1 plus n2 plus maybe 2, maybe 1, I'm not sure the number, divided by 6, I think. Let's see. 2 times 2, 4, times 3. No, that cannot be. So it's, no, I don't remember the number, the formula now. Maybe it is 2, I'm not sure. Okay, I will find the formula and let you know next time. Maybe 2, maybe it's this formula 2. So it's a bit complicated formula, more complicated than SU2. It's, I think. So for example, if I take 1, 0, 1, 0, so this is 1, 2, 3. So there's 3 dimension. If I take 1, 1, it's 1 plus 1, 2, 4, 8. No, this is 4 times 2 divided by 2, 8, correct. Yeah, I think this is the formula. And if you go to higher and higher, SU3, SU4, SU5, etc., this becomes, you need, SU4, you need 3 integers because it's rank 3, no? So the formula becomes more complicated. Long. There's a systematic formula for any SUN. I will stop here. Mainly, I just wanted to give the basic concepts of how one goes about trying to mimic the SU2, the exercises you did for SU2, you know, constructing the representations, how you can mimic that for SU3 and for any algebras. Okay. So, any questions from? I don't know if you are really. I mean, were you all able to hear everything?
Yes, Professor.
How about the rest of you? Because I suspect that some of the connections are not very good. No? For example, let's see. Who are the people? Okay, you are here now. What about Samir? Samir, can you hear? Could you hear? Could you follow all the? I mean, was the connection good enough?
Yes.
Okay. And what about Carlo?
It's fine. I can say everything.
Okay, good. You could hear that. And Ardene Bulgan, could you hear? Hello? Ardene Bulgan? Could you hear? I think her connection is not good. This is a problem. Okay, anyway, so tomorrow you will have the tutorial and I will see you on Monday.